we'll have a Q&A of up to 15 minutes, and after that, a more informal discussion of up to 30 minutes. So without further ado, I'm very happy to introduce Ezra Getzler, who's going to tell us about new results on Batalin-Vilkovisky geometry.
Hello, everyone. New experience for me, giving a nationwide talk. Just a sec. Oh, we're not, okay. I'm a bit new to Zoom. Good. So this is not a talk on symplectic geometry, despite the title. This is a talk on something called odd symplectic geometry. This is a technique, a geometric idea, which was developed by Russian physicists in the early 1980s, Batalin and Vilkovisky, and it works in the setting of supermanifolds. So actually, today's talk is going to be about a geometric structure on supermanifolds, which doesn't really have an analog in regular geometry and is worth studying, I think. So I'm just going to tell you about some new results I have with my former student, Sean Poherence. We're very much focused on trying to apply these ideas to superstring theory, but I'm going to extract just the geometric part of the talk, of the work today, and leave applications to physics for another time. So by all means, in the relaxed 30-minute discussion part, if anybody wants to ask me a bit more about the model that we were applying it to, go for it. So, so as I said, the Batalin-Vilkovisky formalism was developed for studying quantum field theories where there's symmetries or even gauge symmetries which are enhanced in any manner. So this can include supersymmetric field theories, Chern-Simons field theory, and it's had applications also in, for example, the study of the Poisson sigma model, which was used by Kontsevich in formal deformation quantization. That's the work of Cattaneo and Felder, and many other applications in physics. So, so the Batalin-Vilkovisky formalism, really, it's a refinement of the approach to quantum field theory through functional integration. I think a lot of you probably will, in fact, only know the approach to quantum field theory through functional integration, because the other approach through canonical quantization, through a Hamiltonian construction of a Hamiltonian on a time slice, is somewhat out of fashion these days, because it's so much less powerful than the functional integration approach. Now, the problem is that when you're doing the functional integration approach, you're going to have to quotient by some gauge group or symmetry group acting on the space of fields. Or alternatively, you might have some symmetry group like the Lorentz group, which you want to preserve. And on the other hand, it might be that the technique you have for constructing the functional integral doesn't preserve that symmetry. Or alternatively, you could have the problem that the gauge symmetry, it's very difficult to find a representation for the quotient by the gauge symmetry. So they're two different situations that the Batalin-Vilkovisky formalism is set up to deal with. Earlier in the 70s, there was the Becky-Rouet-Storer formalism, which arose as a way of expressing the volume form for the functional integral along the gauge slice. It expressed it as a Berezin integral. I'll define those a bit later. A Berezin integral for some fermionic auxiliary field called a ghost. Later, it was discovered that the Becky-Rouet-Storer formalism was a quantization of Lie algebra cohomology for the Lie algebra of the gauge group. So all of that was known before the work of Batalin-Vilkovisky, and their work, I think in modern language, if you're into this, you could call it higher Lie algebroids on supermanifolds, but or on differential graded supermanifolds. But I'm going to not pursue that point of view. So a typical situation that the Batalin-Vilkovisky formalism can handle which the BRS formalism cannot, is in supersymmetry, it often happens that the supersymmetry is in fact a symmetry of the theory only where the Euler-Lagrange equations hold, the classical solutions of the field theory. Now, obviously, when we're doing quantum field theory, we need to work away from the classical solutions. That's the whole point of quantum theory. So you need a formalism which can extend the symmetries away from the classical locus. And that is, in fact, is what Batalin-Vilkovisky formalism handles masterfully. Even the so-called classical part of the theory gives an extension of Noether's formalism for classical field theory, handling these problems of symmetries that only hold on the Euler-Lagrange locus. So again, I'm not going to be able to tell you so much about all that today, but instead I'm just going to present the supergeometry that the Batalin-Vilkovisky formalism has uncovered as a geometric theory in its own right. And what we'll see is that a lot of the ideas that we're most familiar with in our first course in symplectic geometry, like the Darboux theorem or the Weinstein-Darboux theorem, hold, but the Liouville theorem fails. And that's going to be the center of our discussion today. Okay, so that's the introduction. So what we have to do in the Batalin-Vilkovisky formalism is find a replacement for the Liouville measure. As you know, the Liouville measure gives you in symplectic geometry a way of, if we're given an observable, a function on the phase space, we can integrate it, and that gives some sort of expectation value. Now, in the Batalin-Vilkovisky formalism, instead, we need to find a replacement for that integration, and I'm going to give you a 1-hour course on that replacement today. So in the Batalin-Vilkovisky formalism, first you have to solve the quantum master equation. So I'll explain how that's understood in the modern perspective. And that in quantum field theory, that involves first refining the classical action in order to incorporate ghosts and higher ghosts. So that part I won't be able to tell you about. And then extending that solution to higher orders in Planck's constant, higher loops in Feynman diagrams by performing renormalization. I certainly won't be able to tell you about that. There's actually a book by Kevin Costello, which is an introduction to this formalism in the special case of Yang-Mills theory. So I recommend that book as a first taste for mathematicians of how you can actually perform Batalin-Vilkovisky, this part of the Batalin-Vilkovisky theory. So he doesn't go so much in his book into the second part of their formalism, which is the choice of a Lagrangian in the field space. So somehow the field space in Batalin-Vilkovisky is some sort of, it's called an odd symplectic manifold, and we have to find a Lagrangian which comes down to the choice of gauge fixing for the theory. So the point of my talk today is you can't always find such a Lagrangian. And I'm going to give a more general picture for what can replace Lagrangians in the Batalin-Vilkovisky formalism. I'm going to call those flexible Lagrangians. And right. So I'll be working within Khudaverdian's reformulation of the BV formalism, which is completely geometric. They Batalin-Vilkovisky tended to formulate things having chosen Darboux coordinates, which is very laudable, but Khudaverdian then understood how their formalism has a covariant expression, which I think clarifies beautifully a lot of what's going on. As I mentioned, we'll introduce flexible Lagrangians, and they patch together in a way that's a bit similar to the proof of de Rhams' theorem. I'll leave you to fill in how true that is. Just before I move on, the whole package that I'm talking about here also arises in Donaldson-Thomas theory, where instead of, I'm going to be working in a real C-infinite formalism today, in Donaldson-Thomas theory, instead you're working in an algebraic setting. But a lot of the geometric formalism is similar. You have an odd symplectic structure, and you're likewise trying to understand the analog of the Liouville theorem. Okay, so the application, as I mentioned, that Pohrens and I have in mind is to the quantization of the Green-Schwarz superstring. So I invite you to look at our paper. We don't completely quantize we certainly don't even mention the Green-Schwarz superstring in our paper. We're looking at a toy version of that called the superparticle, which I guess has kind of the same relationship to the Green-Schwarz superstring that the Dirac operator has to the regular superstring. So we aren't getting very deep into quantum field theory in our paper, but the complications are quite sufficient. I'll leave you to sample some of the difficulties that I'm sweeping under the rug today. Okay, so now we get moving. I was advised that I should give a swift introduction to supermanifolds. So let me take the opportunity to advertise the beautiful paper of Lattes from which I learned supermanifold theory, and I don't know of a better source for the subject. He explains which parts of the theory of supermanifolds are essentially the same as that of regular manifold theory, and which parts need modification. Roughly speaking, the part of the theory which needs to be changed the most is integration, and we'll see that a bit later. Okay, so superspaces are Z2 graded vector spaces. All our vector spaces today will be defined over the real numbers. So in supergeometry, we're looking at the analog of manifolds, except locally modeled on superspaces, not on vector spaces. So if we have a superspace, so I was advised to point. So let me see if I can do this. So in the superspace, do people see my pointer? Can somebody tell me?
No.
You don't.
Oh,
there it is. Okay, I have to actually write. Okay, so there's a superspace. The n before the bar indicates the number of even, or a physicist would say bosonic variables, and the m denotes the number of the dimension of the odd part of the superspace, or the fermionic part. Okay, so whenever we have a basis of a superspace, it'll be homogeneous. It'll be some set of even elements and some set of odd elements. If V is a homogeneous element of a superspace, I'm going to use absolute value sign to denote its parity, which is 0 or 1, depending on whether it's bosonic or fermionic. Okay? So there's this famous Kossel sign convention, which I think most people will have met. In fact, all of you will have met when you studied de Rham theory. So just as in de Rham theory, we have the idea of a commutative superalgebra. That's a superspace with an associative product, which is homogeneous. So if you have homogeneous elements, their degrees add when you multiply them. And it's got a twisted commutativity, namely, it's commutative except when you multiply two odd elements, and on odd elements, it's anti-commutative. So what that tells you is if you have a collection of odd elements, they generate, in fact, a exterior algebra inside the commutative superalgebra. Okay? Or maybe if there are no relations, I should say, they generate an exterior algebra. So examples of commutative superalgebras are ordinary commutative algebras, which simply have vanishing odd part of their superspace, and exterior algebras, which are, so in this case, it has an even subspace of dimension 2 to the m minus 1, and an odd subspace also of dimension 2 to the m minus 1. So now I come to the definition of a supermanifold. This is, I fear, going to be too quick for those of you who've never ever seen what a supermanifold is before, but bear with me and we'll see if you can get something from the talk. So underlying the supermanifold, we have a ordinary manifold, which will be n-dimensional, and that has sometimes been called the soul of M. And over M, we have a sheaf of commutative superalgebras. So it's a ringed space, but it's I guess a super ringed space. So locally on the soul, the sheaf of rings decomposes into just smooth functions on some chart, tensored with an exterior algebra. Okay, so you see that you can actually recover the soul by taking the sheaf of commutative, the structure sheaf O, and quotienting it by all the nilpotent elements. That just hands you back the ring of, well, the sheaf of smooth functions on the manifold M0. Okay? So just 1 second. No. Sorry about that. So now let's assume that those open sets in the chart are actually coordinate charts. So they have coordinates x1 up to xn, and then choose also generators of the exterior algebra, and those will be our odd coordinates, xi1 up to xi-m. And essentially, the local theory of supermanifolds, we work with functions of these coordinates, and often we'll find ourselves doing Taylor expansions. The big difference in the subject is any Taylor expansion in the odd coordinates will terminate. So you just have to go to order m in the odd coordinates. If you try to take any further partial derivatives, you'll just get 0 because of the anticommutativity between those coordinates. So we'll say that such a supermanifold has dimension nm. And in Latus's paper, he explains and gives proofs for extension of all the basic techniques that we're used to for studying manifolds to supermanifolds: differentiable maps, Taylor's theorem, chain rule, inverse function theorem, structure of fiber bundles, the definition of the tangent and cotangent bundle. And I would add also the Frobenius integrability theorem actually goes through. So there's quite a big package of stuff. Supermanifolds in many ways have much the same flavor as manifolds. You can define the de Rham complex, but now we get a huge difference. The differentials of the odd coordinates now commute. And for even d psi I, you see it commutes with itself, whereas psi I anti-commuted with itself, so had square 0. So d psi I actually generates a polynomial algebra in the de Rham complex. And as a result, the de Rham complex is unbounded above. It doesn't have a highest degree, and integration is not in supermanifold theory of differential forms, but of something else. So now I'm going to try to explain that. So I just mentioned, I didn't put this in the notes, but one way of thinking of this is that as soon as there are odd coordinates on a supermanifold, it's never orientable. Okay? So the differential forms do not provide any manner of orientation. However, you can still define the de Rham cohomology, and guess what? The de Rham cohomology of the supermanifold is naturally isomorphic to the de Rham cohomology of the soul, because the supermanifold actually retracts in the sense of supermanifolds to the soul. Okay, you can define the tangent bundle. I should have said super bundle of the supermanifold, because its fiber at each point of the supermanifold is a superspace of dimension nm. And in coordinates, you can just use the standard partial differentials as a basis for the tangent space at that point. Okay? So think of it as being over each of these coordinate charts, just a trivialized super bundle, and then there are transition functions as we go from chart to chart, which are obtained by taking first partial derivatives of the transition functions as we go from chart to chart, which are functions of the x's and the xi's. That's the key change in the structure of the theory. Okay, so let me make a parenthetical remark that if you study the theory in the physics literature, you'll learn that all the supermanifolds in the BV formalism have an auxiliary Z grading. And so, and that grading doesn't have anything a priori to do with the parity of the functions in the theory. So it's extremely important to make sure that you don't think of this Z grading that you might find in the physics literature as determining this parity that on the supermanifold. I'm not going to discuss the Z grading in the BV formalism today because it actually has no effect whatsoever on the story that I'm going to tell you. But in principle, you should go back through my talk and sprinkle Z grading on everything. Okay. So before I tell you about odd symplectic geometry, I just want to give you a crash course in Lie supergroups because I think you will appreciate, when you want to study superbundles, the most effective way to do that is via the principal bundle if you want to study vector bundles, the most effective way to do it is to study the principal bundle that it's associated to. And that principal bundle will have a structure group, which will be a Lie group. So likewise, in supergeometry, we're going to think of principal superbundles with structure supergroup, which is a Lie supergroup. We're not going to be thinking about any fancy examples. We're just going to have quite simple, sorry, not simple in the sense of simple, but they're going to be straightforward linear supergroups. So let me just start by saying that I'm sure you know that a Lie group can just be defined as a group in the category of manifolds. Well, if you just copy that into the category of supermanifolds with differentiable maps between supermanifolds as our morphisms, we get the definition of a Lie supergroup. So that would be a lecture in itself, but let me move on. And so just say that the only supergroups we need today are sub-supermanifolds of the general linear supergroup, GLNM. So what is that? Well, we can look at all endomorphisms of the superspace RNM, and that in fact is a, maybe I should have made that clearer. Endomorphisms of RNM is a superspace itself. It's also a super algebra, but not commutative, of course. The even part has dimension n squared plus m squared, and the odd part has dimension 2nm. Okay, and you see they add up to n plus m quantities squared. So now what we do is inside that superspace, we take an open subset. Open, I should have written sub-supermanifold. So let's represent endomorphisms in block form, A, B, C, D. So A is an endomorphism of Rn, D is an endomorphism of Rm, and B and C exchange the two spaces. So they have different roles. A and D parameterize the even coordinates, and B and C, their matrix entries are the odd coordinates. Okay? So this is our first non-trivial example of a supermanifold. We take the open part where A and D are invertible. Okay? And that's exactly the part where the endomorphism of RNM is invertible. So that's a supermanifold. Its sol is GLN cross GLM, and the odd coordinates are parameterized by the matrix entries of B and C. Okay? So, so the structure, the tangent bundle of an NM dimensional supermanifold has structure group GLNM. And given a rational representation on some superspace of GLNM, you can form the associated vector bundle. Well, actually, you don't need a rational representation. It could be any differentiable representation, but in fact, the finite dimensional representations will be rational. Okay, so we need a particular rational representation that may be new for some of you. Turns out that there's that the space of, the group of characters of GLNM, homomorphisms of the supergroup from GLNM to GL1, in other words, maps of manifolds which are compatible with the supergroup structure. GL1 is just a group, by the way, but yeah. So it's, in other words, it's just some even graded function, global section of the structure sheaf over GLNM, which happens to define a homomorphism to GL1, okay? So in particular, on the Sol, it's nowhere vanishing. Let's see what the formula is. Well, the thing is, it's a character. So if I can factorize my matrix ABCD, I can just write it's Berezinian. BER, I should have said its name is the Berezinian. So it's named after Berezin, who discovered it. And so once we factor, you'll see that those two matrices on the right of the equal sign are a factorization of ABCD, right? So the Berezinian of ABCD is the product of their Berezinians, but the first matrix in that factorization is lower triangular, so its Berezinian is 1. And the other one, well, the definition of the Berezinian for an upper block triangular matrix is it's the ratio of the determinants of the two blocks. So that's the definition. And then don't do it during my talk, please, because it's not as simple an exercise as one might wish, but your exercise is to check that this is actually a character, okay? And notice that unlike the determinant, this is a rational character. The determinant is sort of quite unique, I think, in the subject, in that it's actually a polynomial. There's no a priori reason why that character should be polynomial, and in supergeometry, its analog most definitely isn't, okay? So we can form a line bundle. So when I say line bundle, its dimension is 1 bar 0. It doesn't have any odd directions. And it's associated to the character of the structure supergroup, the inverse of the Berezinian. So that's the density bundle, or volume. Maybe I should have called it the volume form bundle. If we put absolute value signs on the Berezinian, because the general linear group has, well, if n and m are both positive, it actually has, I suppose, 4 components. And you could have taken the absolute value of the Berezinian, but I'm not going to today. Actually, Khudaverdian does, but let's leave that aside. So Berezin then shows that there's a covariantly defined integral from sections of this volume form bundle to the real numbers, compactly generated, compactly supported sections. So in local coordinates, we can write a section in this manner. And so you see, I've taken the differentials of the even coordinates and taken their product and divided by the product of the differentials of the odd coordinates. That's, I guess, just a symbol. And then it's multiplied by a function with compact support of the coordinates x and psi. So what you do is you extract the coefficient of psi1 times up to psi by taking this iterative partial derivative. Yes, sorry, go on.
I don't know if this is the same for everyone, but your sound just got terrible. Try speaking again.
Let me start again. How about that? Shall I talk about the structure of the density of local coordinates again?
So I wonder if it's me or if it's you. Can someone else type whether they're getting Ezra's sound okay? The sound is bad. Yeah, something happened just about 30 seconds ago.
Has it come back?
Yeah, now it's good.
I'm back in action. Yeah, well, modern internet. Yes, yeah. Well, yeah, you know what I'm talking about. So, where was I? So you have to take, so this function f, you can expand it in monomials in the psi coordinates, right? And each of the coefficients of those monomials will be a function of x alone. So when you set the size to 0, you get a function of the x coordinates, just a function on the sol. And then you get linear terms in the psi coordinates, and you go all the way up to the top order, which is where you have psi1 multiplied up to psi m. So what we're doing is extracting that coefficient, so thus setting the size to 0 after taking the mth partial derivative, and then integrating the resulting function of the x coordinates with respect to x. So that's the definition of the Berezin integral. And he showed that that's covariantly defined and that it satisfies the natural, so it's it's covariantly defined. Okay. Is my sound back? Is everything okay?
You're good.
Great, thank you. So, okay, finally, we get to the subject of the talk. As I mentioned, there's this notion of a differential form on supermanifolds. So they're just obtained by taking the so you take the differentials and you basically just imitate the definition of the differential forms, except being careful to put the correct signs in. So as I mentioned, what that implies is that the differentials of the coordinates anti-commute with each other, except for the differentials of odd coordinates, which commute. Okay. In any case, a two form determines a bundle map from the tangent bundle to the cotangent bundle by inner product. You can contract a two form with a vector, and you'll get a one form. And we say that a two form is non-degenerate if this map is invertible, and symplectic if the two form is non-degenerate and also closed. I'm going to only in today's talk consider odd symplectic forms. That is, the total parity of the symplectic form will be odd. What that means is that the two form defines a bundle map from the tangent bundle to the cotangent bundle, which exchanges the even and odd parts of those superbundles. So since the cotangent bundle is dual to the tangent bundle, its superdimension is the same as the tangent bundle. So in other words, n and m have to actually be equal in order to have an odd symplectic form. So, what we see is that there's a one-to-one correspondence between the even coordinates and the odd coordinates, and in fact, Darboux theorem, with essentially the same proof. What I mean by same, you'll have to interpret according to your own favorite proof of Darboux theorem, but I have a hunch we all have the same favorite proof. So you get that actually the pairing between the even and odd coordinates is in fact can be viewed as coming through Darboux theorem. They're in some sense canonically conjugate pairs. And the symplectic form is then written in this manner as a sum over these pairs of dx wedge dxi. So when I say that the symplectic form is odd, what I mean is that each factor there has one odd and one even term, okay? So just a parenthesis, which I didn't put in the slides, in the physics literature, one of the coordinates in these pairs will be called a field, and the other one will be called an anti-field. This is the terminology that was introduced by Batalin-Vilkovisky. So they might, for example, denote psi A, they would possibly denote it like that. So if you are curious about the physics literature, also sometimes the dagger is replaced by a star, but in my view, star is overused in notation. So I just mentioned the dagger. Okay.
Ezra, you have a question from Mohammed Abu Zaid.
Oh, great, go for it.
Sorry,
Hello?
I wanted to know, so you said that, in general, there's some kind of extra grading,
Yes.
and this symplectic form, is it going to be, in this general case, is it also going to have an extra grading that you
Yes, absolutely. Thank you, good. So I'll mention it and then we'll move on. The symplectic form always has degree -1 with respect to that Z grading in the subject.
I see.
Thank you for mentioning that, because we'll see in a couple of slides. Let me return to that when I mention Pavel Shevera. Okay, so if I forget, remind me. So if you have an odd symplectic supermanifold, there's a reduction of the structure supergroup of the tangent bundle from the full general linear supergroup GLNN to a linear sub-supergroup, which unfortunately doesn't seem to have any conventional notation. Latus calls it periplectic, but as far as I can work out, that's largely in lecture notes of Stockholm University, and so that terminology doesn't have a very wide transmission. Manin, in his textbook on gauge theory, calls it pi SP, and I actually quite like that notation. The pi in supermanifold theory refers to exchanging the even and odd coordinates in a superspace. So anyway, so for today's talk, I'll use Manin's notation, okay? So Khudaverdian and Voronov noted, it's possible this had been discerned in the literature earlier, but I don't know anyway. If somebody wants to email me an earlier reference, I'm happy to be corrected. That if you restrict the character of the Berezinian from GLNN to the odd symplectic supergroup, it actually has a square root. So if you like, there's a mismatch between the Picard groups or the character lattices. So that's quite a fascinating observation. And of course, having observed it, the proof is relatively easy. In fact, if you have this block representation of the odd symplectic transformation, oh shoot, I'm sorry, misprint. I'll fix that I'll submit a corrected version of the slides after the talk. Yeah, so the square root of the Berezinian of ABCD is given by that formula det A in the very special case that we happen to be symplectic, okay? So miracle of miracles. And what I'm going to be telling you about is some differential geometry that emerges from this observation due to Khudaverdian, okay? So what that means is if you have an odd symplectic supermanifold, then the character inverse of the square root of the Berezinian determines a line bundle over that odd symplectic supermanifold, which we'll call the half forms. So I'll just mention, Khudaverdian uses the absolute value of that character. So he works with the half densities, but it's a minor difference in those two line bundles differ, of course, just by a twist, a discrete twist. So okay, now, so in any case, what this is measuring, this line bundle, is the failure of Liouville's theorem. The analog in ordinary symplectic geometry can be expressed by saying that symplectic transformations have determinant 1. They're not just a subgroup, or the symplectic group is not just a subgroup of the general linear group, it's a subgroup of the special linear group. Nothing like that holds in our situation, okay? So the failure of Liouville's theorem is, in some sense, the origin of the whole study of Batalin-Vilkovisky. So, so now we come to the first remarkable piece of differential supergeometry in the talk. So if we have a Darboux coordinate system, so from what I told you, we can write a half form just as a function times dx1 up to dxn, where we just take the even coordinates of the Darboux coordinate system and multiply them together, okay? So Khudaverdian, in a Darboux coordinate system, he wrote down a differential operator. It's a second order differential operator, and it's given just by this explicit, we take second partial derivatives of the function in this local representation, and then use that to define a new half form. So I think it's almost obvious that this has square 0, because if you take the second partial derivative with respect to one of the odd coordinates, you're going to get 0. So I'll leave you to use, what's the name of the theorem? The partial derivatives with respect to coordinates graded commute. Clairaut's theorem, if any of you are teaching first year calculus this term. Okay, so Khudaverdian proves a quite remarkable result, not a particularly simple theorem. You need to basically have a good grip on how Darboux coordinate systems can change into each other. I think in any case, he proves that this operator is independent of the Darboux coordinate system. So this is some result about G structures, really. So now, if you take one thing away from this talk, it's that there's actually an invariantly defined operator that you might not have heard of before in supergeometry, which I think is a pretty important statement. So Cheverat found a really elegant origin for this sheaf and this operator, at least in the special case where there's a polarization of the odd symplectic supermanifold. For example, if it's an odd cotangent bundle. So I won't define any of those concepts because I don't need them in the talk. But now I want to come back to Mohammed's remark. He was asking about grading. Note that if omega has internal degree -1, well, it's also a 2 form. So 2 plus -1 is 1. So its total grading is 1. And what that means is if we take wedge product with it on the de Rham complex, we can view that as a differential. And so Cheverat observed that the sum of the de Rham differential and exterior multiplication by the odd symplectic form defines a differential on the de Rham complex, and showed, at least when there's a polarization, that that's equivalent to the Khudaverdian operator acting on the sheaf of half forms. So he gives a completely explicit contracting homotopy using homological perturbation theory. And in my view, it's quite an important problem to extend this result to the general case. Well, actually, I know someone who's working on that. Okay, I'll leave it at that. So now, Berend and Fantecchi, in work on Donaldson-Thomas theory, introduced a very nice terminology that if you have an odd symplectic supermanifold and a nowhere vanishing section, a trivialization of the half-form bundle that is closed under Khudaverdian's operator, that's what they called an orientation of the odd symplectic supermanifold. So, so they were working in the algebraic setting, but I'm going to steal their terminology for the real setting. And so we can, in other words, the pair of a odd symplectic form and an orientation, it's local structure, which in addition satisfies a pair of differential equations, namely that the symplectic form is closed and that the orientation half form is closed under Khudaverdian's operator. And we could call that package a Batalin-Vilkovisky supermanifold. And what's absolutely remarkable is that it's the study of these, which is in the modern theory of perturbative quantum field theory, it's in some sense what people who study quantum field theory study. So to give you a tiny taste of how that relationship works, somehow in a Darboux coordinate system, an orientation can be written as the exponential of some function, which will be the Batalin-Vilkovisky action of the quantum field theory. And then the equation of Khudaverdian, or of Batalin-Vilkovisky, becomes the quantum master equation of Batalin-Vilkovisky, which is a second order partial differential equation, although I shouldn't exaggerate in the sense that, remember that some of these coordinates are odd. So it's not a differential equation in the sense, say, of elliptic or hyperbolic differential equations. It's really more of an algebraic structure. So actually in quantum field theory, and this is really the big difference between the story I'm telling you about today and the eventual applications. The action will be expanded as a Lagrange series in Planck's constant, h bar. And the initial term will be a residue of that h bar inverse times S0. S0 will be the so-called classical Batalin-Vilkovisky action. Then we can expand the quantum master equation into a series of equations for increasing genus. And the leading term is the classical master equation. And it turns out, and this is absolutely, to me, extraordinary, that this encapsulates not just all traditional symmetries of quantum field theory, of classical field theory, but also all generalized gauge symmetries, supersymmetries, extended supersymmetries, supergravity, you name it. Everything can be re-expressed as a solution of this equation. This equation is, in some sense, the definition of higher Lie algebroids on graded on differential graded supermanifolds. And so in some sense, the quantum master equation is some remarkable perturbation of this equation. Okay, I'm going to move on from that. That's not so much the topic of my talk today. Okay, so now I come to the actual topic of the talk, which is the construction of integrals on sections of the half forms. So we have this line bundle, the half form line bundle over our supermanifold, and we can look at compactly supported sections of it and ask, how do we construct linear forms on that which vanish on the image of Khudaverdian's operator delta? So let me call such a linear form a trace, and these are the basic linear forms that are used by Batalin-Vilkovisky to define functional integration. So they would take an orientation and apply a trace, and that would be the vacuum expectation. From that, by perturbing the orientation or the action, you can actually access all of the observables and all of the amplitudes of the theory. This is explained in Kevin Costello's book in the case of Yang-Mills theory. So the way that Batalin-Vilkovisky constructed traces was to choose a Lagrangian submanifold. So they took a supermanifold, which is properly embedded in M, such that the symplectic form vanishes along L, and it induces a isomorphism between the tangent and normal bundles. So this is, of course, exactly the same definition as for ordinary symplectic geometry. So this is, there's no, as it were, decorations on the theory of Lagrangian submanifolds coming from the exotic geometry of Khudaverdian. So now, if you do a little bit of linear algebra or superalgebra, you'll see that the half-form bundle of M restricts to the Berezinian bundle of L. That's canonical, that isomorphism. And so you can integrate the restriction of a section of the half-form bundle over L. And their main result is that that defines a trace. Okay, so that's in fact a consequence. Do I say this on the next slide? No, that's a consequence of the Darboux-Weinstein theorem. So the around in a neighborhood of the Lagrangian, you can in fact parameterize the Lagrangian as a section of an odd cotangent bundle by an exact one form, defined by an exact one form. So using that, the proof of the theorem becomes quite straightforward. In fact, by deforming the coordinates, you can replace the section by the zero section. Okay, and again, the proofs imitate those of regular Darboux-Weinstein. Okay, so the point of my talk is that somehow those traces constructed by Batalin-Vilkovisky don't seem to be general enough to handle some of the more exotic quantum field theories that come along, such as extended supersymmetry quantum field theories or superstring theory, supergravity, some of the ones that interest me the most. Essentially, it's because of the spinners in the theory. The definition of gauge fixing when you have spinner symmetries is quite tricky, and it means that you have great difficulty choosing a global choice of gauge. Maybe a physicist might refer to this as an analog of the so-called Gribov ambiguity, the lack of ability in gauge theory, once there's some topology to space-time, to, for example, S4, to choose a global choice of gauge. Okay, so I'm going to introduce an idea which we call flexible Lagrangians, which are sort of local choices of Lagrangian patched together in a particular way. For those of you who are more algebraic geometers, you could think of this as descent theory for Lagrangians. So I'm going to rely on a perturbation formula of Mikhalkov and Schwarz, which gives the variation of integration over a Lagrangian when the Lagrangian lies in a family of Lagrangians. So I want to explain to you how the traces of the traces of Batalin-Vilkovisky change as I move in a nice one parameter or higher parameter family of Lagrangians. So now let's go back to regular symplectic geometry. You'll recall that if you have a one parameter family of Lagrangians, then the infinitesimal deformation of the Lagrangian is determined by a closed one form along the Lagrangian. And the same thing holds for odd symplectic manifolds. If you have a Lagrangian and you take a one parameter deformation of it, the infinitesimal deformation is measured by a closed one form. Well, if you look at the parity of the situation, you'll see that that closed one form has odd parity. And therefore, well, it's closed, but the odd de Rham cohomology of a supermanifold definitely vanishes, because actually the de Rham cohomology of the supermanifold is isomorphic to the de Rham cohomology of the sol. You can retract the supermanifold to the sol. And therefore, this closed one form is actually exact. And it's represented by an odd function on the Lagrangian. So not only that, but that odd function, in other words, an odd section of the structure sheaf of functions. That function is also uniquely determined because there's no constant term for odd functions. There are no odd constants. The only constants are the real numbers, and they're definitely even. Okay. So what that means is if I have a one parameter family of Lagrangians in odd symplectic geometry, I get a family of functions on those Lagrangians. And I can then multiply it by the differential dt in the auxiliary parameter, and I get an object of even total parity, because the one form, dt, I can think of that as odd parity. Back to Mohammed's remark, if the symplectic form had internal degree -1, then actually these functions, eta, also have internal degree -1. And so the total degree of eta dt will be 0. And that'll be important in applications of the formula I'm going to give. Okay, so now let me upgrade that to families with several parameters. So I take as my parameter space the K-simplex, which is a closed polyhedron lying in K-dimension Euclidean space. And now suppose I have a K-parameter family of Lagrangians lying inside my supermanifold. So in that case, I can apply the above construction and actually get a one form on L cross delta K. I should say that this one form, it's only a one form in the simplex directions. It doesn't have any one form components in the directions of the Lagrangian. And it's even total parity. All I do is for each of the parameters, T1 up to Tk, I perform the construction that I did on the previous slide except multiplying by dt1 up to dtk for the appropriate functions. Okay, so now let me just use small Greek delta to denote the de Rham differential in the direction of the parameters. So then our basic formula, which is a global version, an integrated version of the formula of Mikhalkov and Schwarz, is that if you have a family parameterized by differential forms on the K-simplex of sections of the half-form bundle, and you pull it back to this family of Lagrangians, then you should correct the integral by multiplying by e to the minus eta. And with that correction, we now have a chance of producing a trace. So this is really the main formula of today's talk, and which is a good thing because I've only got 4 more minutes. So let me accelerate. Really what I'm saying is that the parameterized families of half forms, that we should work on with the total differential on that, which is little delta plus the Khudaverdian differential. And so we have this, in some sense, what it says is that the integration along the Lagrangian of this modified integral is a morphism of complexes. And the proof just uses the Darboux-Weinstein theorem. It's a relatively straightforward exercise in integrations by parts. So you can find the proof in my paper with Poherence. And so this is going to be a bit heavy, but so now let me just run over the definition of what a flexible Lagrangian is. I'm going to assume I have some locally finite open cover and a partition of unity. So by a flexible Lagrangian, I'm going to mean a whole collection of families of parameterized families of Lagrangians lying inside the open sets of the Czech nerve of the cover. So I would urge you to just work out what all of this says in the special case where I just have 2 open sets in the cover, U and V. Then, of course, it's much simpler. I'm just going to have a Lagrangian in U, a Lagrangian in V, and a 1-parameter family of Lagrangians in U intersect V, which interpolate between the 2 Lagrangians that I started with when intersected with U intersect V. Okay, so there's a whole lot of gluing conditions that we need to impose along the faces of the simplices in order to define a flexible Lagrangian submanifold. You can, maybe some of you can imagine what those are, but let me just skip that over. Okay, so now I'm going to borrow an idea from Sullivan's rational homotopy theory. We can define a Tom Whitney complex for the half forms over this Czech nerve. What we do is we just take, over each open set in the nerve, we just take half forms and tensor that with differential forms on the K-simplex. And then we take a subspace which of those which are in some sense compatible with all the different simplicial maps between the different open sets in the nerve. So I have to rush over that part. This has a differential, which is the de Rham differential in the simplex directions plus the Khudaverdian differential in the half-form directions. And this complex is quasi-isomorphic to the Czech complex of the sheaf, half-form sheaf. Well, in our setting, these sheaves are all fine, so it's just quasi-isomorphic to the sections of the half-forms with differential delta. So I'm going to define a trace on this complex. You can already see, though, perhaps that if we were in an algebraic world, this approach might have some advantages, because it would be very unlikely that we could actually find even algebraic Lagrangians in that setting globally. So this is my last slide. This is too much to absorb, I probably understand, but I'll open up the discussion, leaving this slide visible so you can idly try to follow what it says. But the basic idea is that using the partition of unity on each open set in the check nerve, I can define a differential operator acting on half forms. And so I apply that to the appropriate component of the Tom Whitney form, restrict to the appropriate family of my flexible Lagrangian, throw in the exponential, the correction term of the k-parameter family of Lagrangians, integrate over the Lagrangian, integrate the resulting differential form over the k-simplex, add all of that up over all of the indices, and then the final theorem is that that defines a trace. So that's our main result, and I'm hoping that this will find lots of applications in quantum field theory. Good, thank you so much.
Okay, I invite anyone who cares to unmute themselves and give Ezra a hand. Okay, now Ezra, would you prefer me to call on people, or would you like to do that?
I can call on people. Let's see how it goes. If it doesn't work, we'll shift to you. Okay. Be brave. Maybe I'll have to start calling on people.
Well, I have a question.
Okay.
Okay, so I was wondering, do you have a go-to example of a flexible Lagrangian that's not an honest Lagrangian?
Yeah, but it's in our paper, and it's insanely complicated. It took me 3 or 4 months to find. So I can tell you, though, that it's in the setting of the so-called superparticle. So it involves 10-dimensional superspace, which is Minkowski space in 10 dimensions, times the Majorana-Weil spinors in 10 dimensions. Somehow the origin of supersymmetry in 10 dimensions is that there is a particularly small spinor representation of the Lorentz group, which is 16 real dimensions. Now, let me just quickly run over 10-dimensional Yang-Mills, super Yang-Mills. You have a vector or pseudo-vector, what is it? Anyway, a connection field. That's like a vector field. So it has 10 components, but 8 of them will be physical because it's a massless field. So that's the gluon field. And then we have the gluino, the supersymmetric partner. That'll be a fermion. So we have 16 fermions, and you have to cut down to half of those. So that's the gauge condition. And the difficulty is finding a gauge condition that cuts from 16 fermions to half of that, which works globally over the whole of momentum space. And in fact, it can't be done. So what we do is we have, traditionally, there's a definition that works over most of momentum space, but doesn't work along a single ray in the light cone of the momentum space. And so we need to use another chart over that part. So we have 2 charts and we glue them together, but it's sort of a miracle that we can actually glue them. So yeah.
Okay.
I mean, I should say, sorry, the existence of the flexible Lagrangian is straightforward. It's the existence of an orientation on it, which is the hard part.
I see.
Or rather that the ambient functional integral should be an orientation along the Lagrangian. That's so. I should say that probably the supermanifold M should be replaced by a germ of a supermanifold around the flexible Lagrangian. That would be, yeah.
Okay, and so I should have said before, I'm going to put in the chat window the link to the one question anonymous survey for comments, and anyone who has them should submit them there. And then I see there's a question from Augustine Moreno.
Hello. Unmute.
Hello.
Hi.
Thanks for the nice talk. Just wanted to hear about the applications that you had in mind.
Yeah. So, well, as I said, the main one is the one I was just outlining. So I was talking about the superparticle, which is as it were, a particle moving in superspace. Its action is very, very peculiar. The reason is it's a reduction from. I wonder if you could mute because
Yeah, sorry.
dog. Yeah, and then unmute when you want to talk back to ask a supplementary question. It's a one-dimensional version of the real theory that one is interested in, which is the Green-Schwarz superstring. That is a two-dimensional nonlinear sigma model with target the 10-dimensional superspace. It's an exceptionally beautiful theory, but it's not just a regular old 10-dimensional nonlinear sigma model. It has a topological term, if you like, a WZW term. So WZW terms are, in fact, parameterized by a gerb with curving on the target. And in fact, there's a canonical such gerb, equivariant gerb, namely it's given by the gamma matrices. A gamma matrix has two spinorial indices and one vectorial index, and so it defines over superspace a three form. And so in that, it's that WZW term, that topological term in the action, which somehow causes a lot of complexity to the theory. So yeah, I would add that maybe the other class of applications of this formalism should be to where you have topological terms in the action. That's actually why I introduced the Tom Whitney formalism, because frequently you won't have a global orientation, but you will have an orientation in the Tom Whitney complex. Somehow, maybe this is due to cohomology of the Khudaverdian operator.
Okay, any more questions for Ezra? Okay, I see that Mohammed Abu Zaid has a question.
Great.
Okay, I'm back. I want to ask about the relationship with PTVV.
Yes.
So they introduced these kind of, I mean, of course I'm assuming that I should think of them as like the algebraic algebraic geometry analog of this kind of infinity walk.
Yes.
But they also introduced graded symplectic forms where the grading lives in other parts other than -1.
That's right.
I mean, mostly I want to ask kind of, does this have any relevance for the kind of?
Very good. So I will, so maybe we'll continue, if you have time, maybe we can continue this conversation after the official question and answer, because I'm kind of hoping that Pasha Munyov can be dragged into the conversation, and it'll be easier when we're just having an informal discussion. I have spent years trying to answer your question. And finally, my current answer to your question is that I'm looking at the situation where the internal differential of PTVV vanishes. So they're in a way looking at a derived version of the story I presented today. Does that
yeah, that makes some sense. I mean, yes.
Yeah. So it's very confusing because the classical BV action, that S0 that we had on an earlier page, the S0, I'm sorry, the video window is in my way. Okay, good. That S0 itself does define a differential. A priori, it looks a bit as if it's the differential that PTVV are talking about, but I don't think it is. That differential that arises in the work of Batalin-Vilkovisky, which generalizes the BRS differential, I think that should be viewed as a perturbation of the differential in the PTVV formalism. But it's possible that there are applications of PTVV where a neat separation into, as it were, internal differential and BV differential is not possible. But in this direction, could I suggest the best paper that I know which addresses this in a sort of mathematical, sort of directed towards mathematicians, is a paper of Felder and Kazhdan. So I would warn you that in some sense it's not appropriate. They're looking at a toy version of the theory. They're not looking at quantum field theory, but I think reading their paper will also go a long way to answer what the potential relationship with PTVV is.
Okay. Any more questions for Ezra? Wait a few more seconds. Okay.
Can I ask? I'm unsure. You're going to explain how we go into the discussion room?
Yeah. So what we'll do after Simon's question is we will, I think, maybe pause for a minute and let people who'd like to exit, and maybe a quick bathroom break. And then whoever would like to will come back together and basically continue the questions session, but maybe with a more informal tone, and it'll be more okay to go into detail.
Yes.
Yeah. Okay.
Yeah, I can read the question. So I'll read it out. Is somehow PTVV doing a BV infinity version of my talk? So it depends what you mean by BV infinity. One interpretation of BV infinity would be that the Batalin-Vilkovisky operad is Kossel, and so we have a full Kossel dual of it. That's not the sense. Rather, the BV operad contains the commutative operad, and we don't want to form a resolution of the commutative operad. We want to consider the pair of commutative and BV, and only, as it were, find a cofibrant resolution of that inclusion. Okay, sorry, that answer was definitely not directed at the audience of the talk, but at the particular, a small subset of the audience. But I can go more into that but I would just say that back in the early 80s, when Kossel and Brzezinski developed the theory of Poisson cohomology of Poisson manifolds, that's an example of what I just said. That is infinity. That refers to a resolution of the Poisson operad relative to the commutative operad. So that's what I would think of as being somehow related. On the other hand, I don't know whether this Khudaverdian geometry really, you'll have to, you can try to answer, is that in any way related to BV infinity? I don't think so. But maybe it's quasi-isomorphic to what happens in BV infinity for the future. Okay.
Okay, great. So then let's end the 15-minute Q&A. And let's come back together in a minute or so. And
we stay here, do we?
Yes. Yeah. We'll
okay, good. Okay. Do I have time to make a cup of coffee, or it'd be better to?
How long does it take you to make a cup of coffee?
About 2 or 3 minutes. You can watch me grinding if you want.
That sounds like a great bit of.
Okay. Okay.
It sounds like, yes, you can make yourself a cup of coffee and then see if anybody's left when you come back.
Okay. Sounds like a plan. Okay. I'll be back in a minute or two.